and freezing, just opposite sides of one another. Okay, so back here is where we calculated the phase boundary stuff. Okay, so this was at the freezing point or melting point. The other one was at the boiling point. So what do we do then for the sloped parts? How do we calculate that? Well, that gives us this formula. This is what's called the calorimetry equation. Not terribly important that you know necessarily what that is, but this is the calorimetry equation. It looks really complicated. There's 4 variables here. But once you know what each one is, it's not that hard. Delta E, this little triangle means delta. Whenever you see the sign, it means change in. And so delta E is equal to C times M times delta T. Okay, and remember delta means change in, so it's change in T, and in this case T is going to be temperature. So C is the specific heat capacity. Specific heat basically means how much heat do you have to put into something to cause a temperature change. Okay, units are joules over grams times degrees Celsius. Those are going to cancel out. They seem like really bad units, but they'll cancel out. The M in the equation is the mass, okay, in grams. And then the delta T, the triangle T there, is the change in temperature in degrees Celsius. It's really important to note that anytime you do the delta T there, that it's always final minus initial. Okay, so let me put that in there real quick since I forgot to put that in the notes. Final minus initial. If I can type. Okay, so you always put the final temperature minus the initial temperature. Now, you can get negative signs here, and we'll talk about that in a little bit, but you always want to do final minus initial. Okay, so here's an example of the calculation. So we want to calculate the energy required to raise the temperature of 150 grams of silver from 273 Kelvin to 298 Kelvin. The specific heat is given to us. Okay, so a bunch of stuff there is given to us. We know that the delta T, okay, change in temperature, 298, that's the final, minus 273 is the initial, that's 25 degrees Celsius. You're probably thinking that's actually 25 Kelvin, but remember that Kelvin and Celsius, as far as their distance apart, they're the same thing. Okay, so that takes care of that part. C is given to us. Okay, that is C. Okay, specific heat is given to us. It says specific heat capacity, so that's what that is. Okay, and then the mass is also given to us. Okay, 150 grams. So we're just going to take all those things and basically just plug them into our equation. Okay, so we plug them in. We've got 0.24 times 150 times 25. Okay, and all we're doing there is just taking the numbers from the problem and plugging them in. Okay, and that's going to lead us to our answer of 900 joules. Okay, so relatively straightforward. Here's the deal. If your temperature change involves a phase boundary, then you have to do a couple of calculations. You have to calculate the temperature change part using the calorimetry formula back here, okay, the delta E formula. And then you also have to do the phase boundary part, which is the heat of vaporization or the heat of fusion, the straight up conversion factor problem. So we're going to do one of those real quick. Calculate the energy required to change 1 kilogram of water from negative 5 degrees Celsius to 10 degrees Celsius. So here's the way this works. Basically 3 steps here. Step 1, okay, I'm going to use the calorimetry formula. Okay, delta E equals C times M times delta T. So my delta T, I'm only counting 5 degrees of it because I can only count it up to the phase boundary. If it's water, the phase boundary is at 0 degrees Celsius. So 0 minus negative 5 gives me this 5 here. Kilogram is 1,000 grams. I plug in the C value. I get this answer, 20,920 or 20.9 kilojoules. That's part 1. Part 2 is we do the heat of vaporization. Okay, 1 kilogram. Okay, we take the heat of vaporization of water. We pulled this from the previous slide. So 2,260 kilojoules per 1 kilogram. Okay, kilograms cancel. This is what I get out, 2,260 kilojoules. Step 3 is that I do the calorimetry again, this time from 0 to 10. Okay, because we went from negative 5 to 0. Okay, we did the phase boundary, and then we're going to do from 0 to 10. So 10 minus 0 is 10. 1,000 grams, that's kilogram. Same specific heat. Okay, we're going to plug that in, we're going to get this out, and then we're going to, at the very end, so we get 40.8 kilojoules, we're then going to add all of those together. So we add everything up, and we get a final answer of 2,322 kilojoules. Okay, and actually we should go back here. This specific heat here for water, that's actually not right, because at this point it's ice. It's at -5 degrees, so that has a different specific heat. I think it's 2.1. So that would change that part of the value a little bit, but the process is still the same. Okay, just remember, it is possible to have a negative sign. If you did your delta T's and your final temperature was lower than your initial temperature, then you would get a negative sign, and that's okay. That just means that heat is being released instead of absorbed. Okay, so instead of putting heat in, heat is being given off. That's a couple of definitions that we definitely need to know. It's exothermic if it has a negative sign, which means that heat is released. It's endothermic if it has a positive sign. Okay, exo means outside, endo means inside. So exo means the heat's being given out, endo means that the heat is being pulled in. Okay, that's a lot of stuff, guys. I highly recommend that you go back and rewatch any of this that you need to, and make sure that you practice the calculations. No other way to get this than to practice the calculations.